Hi everyone, my name is Angelos Pelecanos, and today I'm very excited to talk to you about our work with the title Classical versus Quantum Advice and Proofs under Classically Accessible Oracle. This is joint work with Xingjian, Qipeng, and Takashi. The motivating question behind our work is how much more powerful is quantum information from classical? For example, quantum information has a much richer structure than classical information, since it has the possibility of holding continuous phases and magnitudes. However, from what we know so far, extracting all this quantum information is not always easy. Of course, we're not the first to consider this very fundamental question. In particular, many works in the past have asked this question in different contexts. For example, by studying communication complexity, or advice-aided computation. This is when we study computation by considering what happens when we're given the best starting quantum state or classical bit stream. Also, they have considered this in the context of verifying computation using witnesses. Our work focused on the last two bullet points, and in particular for this talk, we will focus on the verification with witness context. Many of you may know this verification question with witness under the name QMA versus QCMA. So let me start by defining what is QMA. So we say QMA is the set of decision problems L in which we're given the following image below, where we have a verifier that is quantum, and it tries to determine whether some input X is inside the language L or no. And it is given the help of an untrusted, all-powerful prover, which provides this quantum witness psi, which shouldn't be too long, should be a kind of short, succinct quantum state witness. And in particular, we're interested in two properties. The first one is that if X is in the language, then there must exist some quantum state such that the verifier given the input X and the quantum state psi should accept. Otherwise, if X is not in the language, then no matter what sufficiently short quantum state the prover provides, V must reject. Now, it is reasonable to extend this definition to QCMA to be the set of decision problems that satisfy a similar picture, but now the prover is restricted to providing the witness as a classical string, again of some efficient size. Again, the properties we care about are that if X is in the language, then there must exist some classical string psi such that V accepts. On the other hand, if X is not in the language, then no matter what classical string the prover provides, V must reject. And these are some very reasonable quantum versions of the very familiar NP complexity class that have been defined a long time ago. And since the definition of these two languages, it has been a question of studying the differences between them. So how much more power does a quantum witness give you over a classical witness? In particular, Aronson and Kuberberg in 2007, they provided a black box separation between these two classes, QMA and QCMA, using a quantum oracle. You can think of a quantum oracle as some unitary in the sky, which we can query by giving quantum states and obtaining the response back. More than a decade later, Pfefferman and Kimmel provided a black box separation with an oracle with a classical description that is distributional and in place. And then more recently, Natarajan and Nerg provided a black box separation, again with a classical oracle with the distributional property. The exact definitions of these non-standard oracles will not be very important for this talk. However, I should mention that our goal as a community is to obtain a separation with respect to a classical oracle. And so I am very happy to report that from our work, we managed to obtain a black box separation with a classical oracle. That is an oracle that is basically a classical function that gets classical inputs and gets classical outputs. So before you cue the confetti, let me also say that our separation only allows the verifier to access this oracle with classical queries. Let's talk a little bit about this. This is what we mean when we say classically accessible, classical oracle. And in particular, our black box separation with such an oracle. What does it mean? Consider on the right-hand side, the image, the very familiar image of a verifier interacting with an oracle O. So as we can see, the verifier provides as a classical string some index I, and the oracle O, which has a classical description, provides its content on this index I. So this is what we mean by classically accessible. And contrast this to quantum access when the verifier, which is quantum, can provide as a query a quantum state that may contain many indices in superposition. As we see there, it could have many indices with amplitudes alpha I. And then the oracle will give back a quantum state that contains its contents on the queried indices, again in superposition. So for example, if the verifier asks as a query a quantum state that is the superposition over all possible indices of the oracle, then the answer from the oracle will contain, even though in a very small amplitude, the entire content of the oracle. So then what is the difference between classical and quantum queries? First, it's very easy to see that classical queries restrict the access to the oracle, since now we only have to ask for one specific index instead of a superposition of indices. And thus it holds that a classically accessible classical oracle separation, what our work shows, is as a statement incomparable to a classical quantum query oracle separation. And I want to emphasize that it is not weaker. And this is because classical access to the oracle makes it easier to show that the language is not in QCMA. However, classical access makes it harder to show that the language is in QMA. However, still, quantum queries to a classical oracle is the gold standard that we are hoping to show. And why is this? Well, say we obtain an oracle separation. Again, the image is a verifier that interacts with an oracle in the sky. And ideally, at some point, we may want to instantiate this oracle, which means that we will replace this classical oracle with a classical circuit that gives the outputs of the oracle. And then giving access to the oracle means that we provide the circuit to the verifier. Now, the quantum verifier as a quantum circuit, it's allowed to embed the circuit CO inside its own circuit. And thus, since it's there, there is nothing stopping it from providing inputs to CO in superposition, thus quantum queries. So we believe that quantum query classical oracle is the more realistic model, and we hope to obtain a separation in that model. Still, let me talk to you about the results with a classically accessible classical oracle. So using similar set of techniques, we prove the following three results. First, there exists a classically accessible classical oracle O1 such that VQP, Q-poly, and BQP-poly are separated. I never defined these two classes, but they're related to the study of advice-aided computation, where one is given a quantum state as at the beginning of the computation, the best quantum state that they can get at the beginning of their computation, or the best classical string at the beginning of the computation. Second, there exists a classically accessible classical oracle, O2, such that QMA and QCMA are separated. So this is the result that I talked about in this talk so far. And the third result is that there exists a distribution and oracle O3, such that QMA and QCMA are separated. And the reason I mentioned this result is because we managed to reprove the statement originally proved by Nadarayan and Nerk not too long ago, using a different set of techniques. Let me move on to some more technical content. As I said, all three of our results use similar ideas and techniques. For this talk, I'll focus on our second result, which is the separation between QMA and QCMA under a classically accessible classical oracle, O. And our constructions draw heavily from the Yamakawa-Zandri problem, and some follow-up work by Qipeng Liu. The Yamakawa-Zandri problem, let me introduce this problem to you. So the main theorem states that there exists an error-correcting code C over n symbol words, and a function that's related to this error-correcting code, fc, such that relative to a random oracle h, it holds that it's easy to invert any image y in this function f if one is given quantum access to the oracle h. On the other hand, it's hard to invert the function if one is only given classical access to this oracle h. The function is explicitly defined as follows. It's not crucial what's the exact format of this function, but you can think of it that it assigns random labels, random n-bit labels to the code words of C, and otherwise it outputs both. Then Qipeng Liu, in a follow-up work, he showed that the same function, fch, is easy to invert if one is given quantum advice, so some quantum state advice, and no queries to the oracle h. But it remains hard to invert if one is only given classical advice and no queries to the oracle. And the idea behind this theorem is that quantum advice actually contains everything you need from the oracle, whereas classical advice is not enough to get everything you need. The main lemma in our work, you can think of it as combining these two works together. And in particular, we show that the same function, fch, is easy to invert with quantum advice and classical queries to the oracle. But it remains hard to invert if one is given only classical advice and classical queries to the oracle. The intuition behind why this lemma is correct uses the very beautiful framework of pre-sampling, which implies that an adversary that is given T classical queries and S classical bits of advice for a random oracle problem behaves very similarly to an adversary that is given T classical queries to the same random oracle and an additional S times T bits of ordinary advice. And here by ordinary advice, I mean just input-output pairs of the random oracle. Thus, one can kind of put together the input-output pairs of the advice into the classical queries, and as long as S is not too large, the number of classical queries doesn't change a lot. I would like to remark that the above theorem doesn't hold for quantum queries. So we generalized Qipeng's result from no queries to classical queries. One may wonder, can we change these to quantum queries? However, the statement of Yamakawa-Zandri says that this is not possible because once you're given quantum access to the oracle H, you can already solve and invert the function f without the need of any advice. And the reason I mention this is because this is one of the reasons why our techniques stop at classical access to the oracle. So let's proceed with the oracle constructions. And let's start with the following warm-up TOE example. We're asking a quantum verifier to decide whether an oracle O small is either completely filled with ones or it has at most 1/3 fraction of ones. Many of you will realize that this problem is actually easy. In both cases, you don't even need a witness to distinguish between the two. Just randomly sampling the contents of the oracle suffices. Thus, let's introduce the Yamakawa-Zandri problem to make the problem a bit harder. And the idea is to replace this small oracle O with a much larger oracle and place the original contents of O small at the indices that correspond to solutions of the YZ problem. That was a mouthful, so let's see an example of that schematically. Here is at the top our small oracle O small, and below is the much larger oracle O. And then we're going to take the contents of O small and place them in these different positions at the larger oracle. And it turns out that these indices that we place, the original contents, correspond to output-input pairs of the YZ problem. And in particular, T, V, such that f of v is equal to t. And let me give you a very high-level intuitive idea for why this works. Well, if one is given a quantum witness from Yamakawa's Andri, follow-up work by Qipeng, and our main lemma, we show that we can obtain as many solutions to the YZ problem as we want. This translates to obtaining many indices that contain the original contents, and thus we can query the contents of the original oracle Osmo. On the other hand, if we're only given classical witness, then we know that we cannot obtain any solution to the YZ problem, and thus we do not have access to the original oracle Osmo, and thus we cannot distinguish whether it's full of ones or at most a third ones. And let me just give you the formal oracle as well for completeness. Our oracle is defined using the following three parameters. First, the random h, which is the same as the one used in the YZ problem. Then we have a random function g that basically randomizes the labels, the images of the YZ function. And this is really only used in the technical section of the proof. And we also have the subset S. And then O is defined by taking as input some output input pair, and it outputs 1 if it's a valid YZ solution, and the output is not in S, and 0 otherwise. And so what does this mean? Well, recall that the oracle is indexed by output input pairs, T, V, and you can interpret this as the zeros of O small lie in S. So we only output 1 if it's a valid YZ solution and it's not an S in the original oracle Osmo. It's not a 0 in the original oracle Osmo. So again, let me complete this discussion on why we need classically accessible classical oracle. I would like to say first that our construction does not clearly break when we allow quantum queries, but rather the current analysis argues that classical queries leak very little information from the oracle. Recall my remark during the main lemma. And we do not know how to show this with quantum queries. Since the main lemma cannot be extended with quantum queries, it seems that maybe a different route has to be taken to prove the result for a quantum access classical oracle. So we're nearing the end of this talk, so let me leave you with some open questions and some final thoughts. As a summary, we translated the search problem of Yamakawa's Andri to a decision problem, and that gave us a number of black box separations relative to non-standard oracles. So it's a reasonable question whether we can use the very powerful tool of Yamakawa's Andri to get any other separation results in complexity theory. Of course, the main question is, can we extend our result to a quantum query classical oracle separation between QMA and QCMA, or BQP Q-poly and BQP poly? And maybe the way to do this is by combining our techniques with the prior work techniques, since they really use a very different set of techniques. So maybe we can learn something from each other. This is the end of the talk. Thank you so much for watching.